Okay, so our next speaker is Karthik Duraisamy from the University of Michigan. And Karthik, why don't you switch there?
Okay. Thank you, Steve, and thanks to both you and Nathan for inviting me to this workshop. I find myself giving too many high-level talks recently. I appreciate the opportunity to do something a little more. All right, so I want to start the presentation by acknowledging my graduate student, Koopman, who did most of the work. Actually, that's unfair. He did all of the work, and this person did his work. And Shao is actually watching this live stream, so hello, Shao. If I have any difficult questions, text me. Yeah. Anyway, so the title is Physics Informed and Probabilistic Learning of Linear Embeddings. So physics information will actually come in 3 or 4 different places in the presentation, so I think it's important. But first, let's start with the why and the what of linear embeddings. So why do we need these, and what is the Koopman operator? So typically, we start with a dynamical system. When we given a dynamical system, x not equal to f of x, we are used to looking at it from a geometric viewpoint. But Koopman approaches this from the viewpoint of dynamics of observable. Okay, so if you have some observable h, this could be some functional of your state. The action of the Koopman operator kt on that observable takes advances that observable in time by a time t. Okay, so that's the fundamental idea. So the nice or the most elegant and amazing property of the Koopman operator is that it is linear in a global setting, right? So you don't have to linearize the dynamical system point by point. You can do global linearization. And now that means you can actually have a linear replica of the dynamics of the observable with no loss of information in theory. So here is a cartoon. So your dynamics is evolving in some nonlinear manifold, and the linear embedding, the observable is evolving on a linear space. There's always a catch though. The catch is that even though there is a Koopman operator, it is infinite dimensional. Okay. So it's challenging to compute it, but if you do compute it, applications are many. You can use optimal control, model decomposition, even model reduction. So I want to start off with a simple example to motivate the power of this linear representation, but also later in this presentation, this will become very relevant when I construct my neural autoencoder decoder with a certain property. So what I have here is a 2-state dynamical system. This is a van der Pol oscillator. It has cubic nonlinearity. And I have replaced that nonlinear dynamical system using a linear model based on Hankel DMD. Okay? If you don't know what Hankel DMD is, it's very, very simple. You take the state, you stack time-delayed versions of the state, and then you find the best linear model. So what is impressive is not only are we recreating the dynamics completely, actually you can get to mission precision. The snapshot data that I used is just shown in green, right? So I've used less than 1/5 of the cycle, and I trained my linear model to replicate precisely the dynamics of this nonlinear model, and it's able to do perfect prediction, right? And if you're interested in details, this paper has some nice descriptions of why this is possible and how many time delays you need. Okay, so now let's set the stage for our linear embedding. So we're going to work on the assumption that we rely on the existence of spectral resolution, and we're going to ignore continuous spectrum. And continuous spectrum can arise in many situations when your state changes rapidly or we have chaos. But at least for this work, we are not taking that into consideration. It's not to say that the tools can't respond, but we cannot guarantee anything. And then we also assume that the eigenvalues are simple, but the most important thing is that we're going to find a finite dimensional representation. So in what context? So you're given an observable h. We want to find this minimal Koopman invariant subspace of dimension d. So phi are your Koopman eigenfunctions. So we want to find this in such a way that if h is in that subspace initially, you hit it with the Koopman operator, it still lies in the subspace. And the nice thing about the Koopman decomposition in that circumstance is that you get a very elegant decomposition, just like the eigenvalues and eigenvectors in linear systems, but you have these eigenfunctions, and these Sj are the Koopman modes, right? So if you change the observable, the only thing that changes is these Sj. So what are we addressing in this work? So this is what we are set up to do. First thing is we want to find the best ways to learn the Koopman operator in a continuous setting, continuous dynamic resistance and not discrete. The second thing we're going to address is how best can we use the knowledge of the physics, in the sense that if you know the governing equations of the original dynamics, how can you use it? Even when you don't have any data. But then there are also situations where you may have data trajectories. So how can you change design architecture to look like that? This is important. How can we enforce stability inside this architecture that has very complicated neural networks, encoders, decoders, things like that? And the fourth point is something that has been bothering us for a long time. It is, we're trying to discover an infinite dimensional operator using a whole range of assumptions. And we need to quantify the uncertainty, right? So how can we get a handle on that? And then, of course, how can we construct these reliable and robust learning architectures, which is the architecture should be cognizant of the limitations of what conventional autoencoders do. So, so we're going to take the autoencoder approach, which I think we've heard 3 or 4 times already over the past couple of days. We have some wrinkles on it, but the basic idea is the same. And other people have also looked at this. I'm pretty sure this list is incomplete, even based on what I saw over the past couple of days. But there are some new elements that we bring in, and even in the autoencoders, we have some new structures that I highlight. Okay, so let's talk about the continuous setting and how we can use the physics information, how we can begin to use physics information. Okay, so we seek this space of Koopman eigenfunctions. And if you write the differential equation for, if you basically take the time derivative of the Koopman eigenfunctions, just using chain rule, you get this expression, and we know that dx by dt equal f from those governing equations. So this last 2 relationships encode basically the relationship between the Koopman eigenfunctions and the dynamics and the Koopman operator, right? So that's one thing. There are some details here, but that by itself is not enough. There are many reasons why we need an identity mapping in the encoders, because one reason is that we want to recover the state, and the other thing is to actually regularize the loss functions. Okay? So with this in mind, we can begin to pose these loss functions. So we have, say, let's talk about the data-free setting, right, where you know the model equations. And what you can do is you can ping phase space, maybe randomly, at these m locations. And then this is how the loss function can look like, where the physics is now encoded here. So this is the expression that I showed in the previous slide. And this is basically the decoder and the encoder reproducing the state snapshots. Okay, so that's when you don't have data. And of course, both the phi and the psi are both parameterized using neural networks, and these are the weights of the neural network. Now, there may be other situations where we may have data, and data may be trajectories. And again, you may have m snapshots of data, and each of those m snapshots may have some small n or tm sequences, right? So if you have one trajectory with, say, 100 snapshots that are consecutive, then tm is 100 for that specific trajectory. In that case, we can directly use this evolution, okay? And you can build it out how many trajectories you have. And so anyway, so that's how we begin. But then now we introduce some of the other wrinkles that I mentioned earlier. The stability is a very, very important aspect here, especially if you want long time integration. You don't want these things to blow up. I think one of the approaches yesterday pursued the Lyapunov route to ensuring stability, but we have a much simpler way of getting there. So what we do is we propose that the Koopman operator is parameterized in this form, right? So you have negative sigmas in the diagonal, and then you have some kind of skew symmetric representation. Okay, so this seems somewhat arbitrary, but if you look at this paper, which is going to be an archive this weekend, so we show this theorem that we have any real diagonalizable square matrix, let's say the true Koopman operator matrix, and if the true operator matrix has all non-positive real parts, then you can actually show that this specific parameterization gives you a K that is similar, K stable, the stabilized version of it is similar to K. Okay, so the nice thing here is we get unconditional stability at the same time we don't lose any expressivity. Okay, so that's one info. And the second thing is, I think you could say we got inspiration from ResNets, but in fact we connected this to ResNets only later. But the general idea comes from, if you want to think about it from a high level, you can get an analog with ResNet. So what are residual networks? So these are extremely popular learning architectures proposed in 2015, and yesterday I checked, it has 25,000 citations. So it's just taken off, and it's a very, very, very simple idea. And in fact, a computational physicist, it's like the most basic thing you can do, right? So what it does is, effectively, instead of learning the full map, you skip a connection. And so it basically gives you identity mappings perfectly, and you learn the residual that is left from the identity mapping. So very simple idea. And that gives you a lot of benefit in both training, time, training errors. And if you look at the visualization of the loss function using, I don't know what fancy methodology this is. So without skipping connections and with skipping connections, these are the loss statistics, right? So it is intuitive and it is very useful in practice. And so we want to sort of enforce this kind of property in our decoders, in our autoencoders also. And so our inspiration again relates back to the first example that I showed, where the linear embedding really captured what was going on in the nonlinear dynamics. So we want to make sure that our encoder has at least that property, and we just learn the residual of what's left. So the procedure is very simple. First, you compute the R dominant singular valued decomposition modes of the center snapshots of the data. And then if you're doing straight DM, so then you have Q, where the basis you get from the SVD is VR. And then if you're just doing straight DMD, you find the best fit linear matrix. So that's now included in our solution. And then you do input normalization, where the scaling is the standard deviation of the snapshots. So now your scaled inputs, Q, is written in this form, and this becomes the DMD basis. Okay, so this is like the residual net. That is preserving the identity mapping. You're specifying that there is this encoder that's already built in. So the job of the neural network is just to learn the residual of basically what is left out from this representation. Maybe this is too complicated, but so if you want to look at this from a deterministic setting, here you have your two normalizations, and then so here is your ResNet type architecture where you're just learning what's left out. And then so this enforces the dynamics and this enforces the So if you want to look at it more specifically, so that's the part of the loss function that's focused on reconstruction, the part of the loss function that's looking at encoding the dynamics, and here is the regularization terms. Okay, so the last part is uncertainties. So naturally we go to Bayesian deep neural nets. So again, fundamentally the idea is simple. We treat all the parameters in the network as uncertain. And given some data or samples, we can use Bayes' theorem to get the positive probability of the parameters given the data. If you want to do it perfectly, at least if you want to pose the problem in the most rigorous way, you want to minimize the tail divergence, but that's impractical. So we go via the evidence lower bound route, which makes the problem simple. And on top of this, we apply the mean field approximation. So effectively, we are looking for a best fit PDF for the true position. And the engine that's powering it is again, standard tools, TensorFlow and Edward. And again, the last bit of detail on how we set up this Bayesian inversion. Again, so priors are all Gaussian, centered at 0, and then there is some covariance here. And then the likelihood function, again, has the reconstruction part and the dynamics part. And Shawu has actually constructed this in a hierarchical Bayesian setting, so you can actually account for the impact of the assumptions you made in the priors as well. Okay, so let's go to results. The first one is a pi example. We call it the Brunton problem because that's where we learned about Koopman in subspace. So it's a very simple problem where you know analytically how things should look like. So that's your dynamical system. It has a slow and a fast manifold. So this is a layer structure for this specific problem. We use optimization, the Adam optimizer. And again, remember, this is in the data free setting. So you just ping phase space with as many samples as you want. And without going into details, it looks like it should. But then, this is the part that I always wanted to get to is, we can always get these predictions with what is the uncertainty, right? This is so for some unseen trajectory, this is the posterior samples. We just use straight Monte Carlo MCMC here. So this is the true dynamics that we want to predict. And if we just use 800 sample points in phase space, you get this type of uncertainty. Use 1600, you get this. Use more points, it goes down. So that's a nice thing for us to see. A slightly more complex example, we go to 2D compressible Navier-Stokes. Shawu is working on more complex problems, but at least we wanted to do justice to the Bayesian, so we didn't want too much complication when we are testing things. So he did two things. One is he directly did not work on the Navier-Stokes directly. He did the simulations, got the POD snapshots, and he was looking to find the linear embedding for the dynamical system as described by the evolution of like 50 POD modes. And he used 650 snapshots, right? So here we are not sampling, we're actually using trajectory information in the form of 650 snapshots. Again, to make things a little more interesting and also to gauge the impact of more real-world difficulties, he added Gaussian white noise to the POD mode data. Okay, so note that he did not add white noise to the original flow solutions because that would be easily filtered by the POD, but he added noise to the POD snapshots, and he used the network in the recurrent form with 100 trajectories. So the PM that we described earlier is 100. And there is some neural network structure here. And this is how this is how the eigenvalue plots look like for different Koopman eigenvalues for different signal to noise ratios here. Okay. So again, quite interesting to see that when you change when you increase the level of noise, things just move around all over the place. So again, there could be better ways of handling this, but at least this is how sensitive our methodology is to varying levels of noise. And again, these are trajectory predictions for each of the modes with various levels of noise, but the slide is too busy. It's just that we can quantify the uncertainty, so that's the message. And then we can have some very nice things. So what is shown here is the true flow field and here is the projected flow field on the 50 modes. So this is the data that's going into the learning architecture. And this is the prediction at some time corresponding to the exact solution with some level of noise. This is with more level of noise. So it's not distinguishable to the eye. So this is the velocity magnitude that's being shown here. But now this is the standard deviation as a distribution in space, right? So this is effectively the uncertainty represented over the entire field. So this is very nice, and again, makes me a little more comfortable to think of these things and quantify the impact of many of the assumptions we made. Okay, so last slide. So again, we use these deep neural nets. We leverage this power of expressibility of these methods, and we develop this linear embedding. So there were two forms. I focused mostly on the differential form, where you know the governing equations and you don't have data. But there's also the recurrent form that at least I showed the results for. The guaranteed stability is a nice property. And just like ResNets, we encode what we know. And that's helping us in a very big way. And we have a methodology to quantify uncertainty as well. And we thank the sponsors. And I can take questions.
Great, we got time for some questions. Yeah.
So in your Bayesian neural net study, did you also learn the uncertainty of the data? Or no, that was not it?
I mean, uncertainty of the data. Yes, I mean, it's fundamentally built in. But if you...
Because what Bayesian learning learns, it's the uncertainty of the weights. And then if you write the posterior distribution of the prediction, the terms that are related to the precision of the weights, they go to zero. But what we're left with is the precision of the data that has to be given or learned.
Yeah, so I mean, one way of doing this is being more careful with the priors. I mean, it is true that it is hard to disambiguate the two. I mean, it's hard to separate the things from each other, but under certain assumptions, I think we can handle it. But definitely, I don't have a way of saying this uncertainty is coming from the data, and I know exactly how to. Okay, so let me put it this way: if we know exactly where the uncertainty from the data came from, or what was the experiment that generated the data, then we could encode that properly. But otherwise, it's up to an engineering guess on what we can put in the priors.
Any other questions? And maybe Ben can set up well.
One quick one though. So at the beginning, Koopman is like correctly global linearization under infinite dimensions, but then you found the way to do that. There's certain finite dimensions in certain cases. What were the cases for the finite approximation?
So first you try to find a subspace where so let's say you're interested in an observable. You want to find a subspace where you can represent an observable to a reasonable degree of accuracy. And then if the subspace is good enough, then the observable evolves only on that subspace. And the control parameter for that is, of course, everything that is constraining the problem, but also we also specify what is the number of dimensions you need for that subspace. So yeah, I mean, we are guessing to a degree, but things like training errors, so the learning process is constrained by how much error you can tolerate.
Okay, well, let's thank Karthik again.